Everybody, very briefly, welcome to the panelists. Thank you for participating. Thank you to Daniel Shilton from Airbus for handling the moderator responsibilities, and thank you to Airbus for, on the one hand, giving Daniel a bit of time off. Not that it's any less stressful, I think, than working at Airbus, to be a moderator on this panel. And thank you to Airbus Corporate for providing important financial support for Astro. So Daniel, over to you, and have a good panel.
Thank you very much, Jeff. I have the pleasure to moderate a panel again, and I'm very happy to have four fantastic speakers that are going to tell you about testbeds and analogues. As you know, we are designing, building, testing systems that operate in unique environments, and sometimes building the environments to do that, to test those systems, is as hard as building the systems themselves. So our four guests are in a perfect position to tell them what they're doing in this field. I will briefly introduce them, and then they go off and present their own test bed or analog. And hopefully after that we have time for questions, and I'm really soliciting a lot of interesting questions from the audience, and want to try to make this as a lively discussion as possible. So Dr. Mick Faragalli from Mission Control Space Services. We have Professor Kaley Walker from the University of Toronto, Professor Anton de Ruiter from Ryerson University, and Philip Ferguson from the University of Manitoba. Mick, you're first. Take it away.
All right. Okay, I have a couple slides to share, so I will just bring those up right now, and then I have a special surprise. Can everyone see my screen?
You're good.
Okay, so my name is Mick. I'm the CTO of Mission Control Space Services. We're a space exploration robotics company based in Ottawa, and we were founded about 6 years ago now. And we focus on software development for mission operations, onboard autonomy, and AI. We're a team of about 20 people, and we are hiring. So any students listening in, I know I was a student listening in to Astro a few decades ago. We are hiring, so have a look at our job posting site. Just a little plug there. But I don't want to talk too much about my company. I want to talk about our indoor, lunar, and planetary analog testbed. It's about a 4,000 square foot testbed located at our headquarters. And we really focused on making the testbed geologically relevant and visually relevant, because our focus has really been on developing systems to operate on the lunar surface. So whether that's training computer vision algorithms, doing operations testing.
May be necessary, but reduce it to one if you can, possibly.
Oh, was that a comment for me?
Yeah, just one, if you have more than one browser window open, can you just close any others, because your voice was being halting. And I guess we should all turn off our cameras except for Mick. Fire at will.
Okay, all right. Well, you know what? I might just do one more slide and then kind of do something kind of fun here. We use this facility for our own R&D purposes, but we also lease it out to people who need to use it, whether they want just to use our facilities or actually use it to control a rover, whether it's their own robotic platform or plugging into our plug-and-play mission control software, which allows you to operate a rover really from anywhere in the world. To do whatever kind of R&D that you wish to do, or operations, or even education and public outreach. But I'm going to keep it brief, because I think I have something a little bit cooler to show than a few slides. Let me just have a look here, and if you could still see my camera feed, I'm actually on the moon right now. So this is our facilities, and we really focused, as you can tell here, on creating realistic lighting conditions. Having a single spotlight allows us to create shadowed environments, which is really important when it comes to rover navigation on the surface of the moon. We have geologically relevant features, rocks, craters, outcrops, so that whether you're doing science operations or automated detection of these kinds of features, we build data sets or let you use these things operationally. This is really kind of be the bedrock, pun intended, for some of these future Canadian space robotic developments, such as the micro rover program. I'm not sure if I'm at 7 minutes, Daniel. I'm happy to keep showing footage of the moon yard, but if you want to cut me off, I'm okay with that.
No, you still have time.
Okay. All right. Well, I'm going to walk around a little bit here. This is about 30 meters in depth that you see behind me right now. And while that doesn't sound like a lot of folks go up to the Arctic or various other environments for their rover testing. When we talk about the kinds of speeds that rovers are going to be driving on the moon, we've done some fairly high fidelity operations testing with partners around the world who are launching rovers to the moon in the next coming 1 to 3 years. And you can get a good solid 8 to 12 hours of high fidelity operations in this kind of environment. And if ever any of you have operated a rover for that length of time, that's enough time to really learn how best to do these operations, how autonomy can help you achieve more efficient operations. And and this whole terrain is reconfigurable as well. And based on the location on the moon that folks wish to travel to, we can add in features that make it more relevant to that. We could also turn on the overhead lights, so it's more the lighting conditions more relevant to equatorial conditions on the moon. How's that?
Excellent.
Excellent.
Yeah. I'm sort of jealous, Mick. So. All right, Kaley, you're next.
Okay, so let me see if my screen will not allow me to do what I thought it was going to let me do. So let me switch up. Sorry about that. So what I'm going to do right now is look at a different perspective of things. I'm a Canadian professor who works in physics, and I do atmospheric physics. So I study the composition of the atmosphere in however many different ways we could possibly do that. So whether that's from space, from the air, from the ground. It was mentioned traveling to the Arctic. I do that. That's really fun. I get to work at the Polar Environment Atmospheric Research Laboratory in Eureka, Nunavut, about 1,100 kilometers from the pole. And my team are the ones who are great because they get to go at sunrise when the temperatures are quite, let's say, cooler than they are these days. So let me see if my sharing is not working. Wow, I'm very sorry for this. It's been a busy day of teaching. Okay, so can we see this now?
You're good.
Excellent. Okay, so I mentioned that I do atmospheric science. I'm going to talk about what we do in the atmospheric science community, primarily from the air. So this is a nice example of one of the first flights that I did as PI from Timmins. I also am very involved in space from the side of being the deputy mission scientist for Canada's SciSat mission. That's the atmospheric chemistry experiment. We're in year 18 of a 2-year mission, which is great because that's nice Canadian technology that's been working really well. And we measure the most species that have ever been measured from space simultaneously, which is about 74, which is great. I also am the external co-chair of the CSA's Atmospheric Science Advisory Committee. So that's another thing that I'm trying to bring to this conversation is really representing my community. So I've done a lot of ballooning, but I'm also going to bring in some other aspects from what different members of our community use. So for those who don't necessarily balloon, this is an 18-wheel truck here holding our helium. That's only the top 20th in volume or quarter of the length of the balloon that we use. It's about 25 stories tall. So 110,000 cubic meters. And for scale, these are some of the CSA guys out front. So my next slide should be, why do we do this? Well, we like balloons and aircraft for sort of 2 reasons. One is for getting us to new mission development, and the other is for validation. So giving us different perspectives on the atmosphere. So on the side of the new mission development, it's really advancing TRL as much as we possibly can. Testing a new observation technique we think is interesting, but it's a lot cheaper to put it on a balloon than it is to convince someone to put it in space. Also, it's important for us to get prototype data. So not only just building the instrument, but getting the data and seeing what we can work with, how it works in models, how we can get the most out of the spectral information that we're collecting. And also on the validation side, you need to be able to know what you measure from space is good and continues to be good, because in year 18 of a mission, there's going to be change in your instrument. So you want to make sure that you can continue to have these anchor points and measurements to know how good it is. So shown here on the left is an in situ instrument that my group and I have built. This is a collaboration between University of Toronto and University of Alberta. This thing in the front, which is covered in mesh, is basically two mirrors, and we bounce a laser back and forth between them 112 times to get 81 meters of path difference. So we're just basically doing an absorption experiment, and we change our gas sample as we go up in the atmosphere. Some other examples of flight projects. So that was the Kaley that flew in 2018, 2019, and we're going to fly again with a new version of the instrument in 2022. Also Parabol, which is this mission here on the left. I had 4 different instruments, 2 from the University of Toronto and 2 from York University. And we were looking at absorptions in the atmosphere, and we used the solar occultation technique, which is what we use on SciSat. So basically we scan the atmosphere as the sun comes up or goes down and use that to get profile information. Also within our community, there are a number of other projects that we're involved in, and I'm picking out a couple of them that I have some relationship to, but I'm not leading. For the proposed Arctic Observing Mission, which is being led out of ECCC, the IFTS is being flown on a balloon next year, and that's an instrument that's been developed through STDP. And then also we have a suite of 3 instruments, which have been proposed to be part of NASA's Atmospheric Observing System, which was part of their decadal survey. And that's going to fly in 2 summers on the ER2, which is a refurbished spy plane, which can get you to 20 kilometers. And is really nice because you can sort of simulate how your instrument flying through the atmosphere on a satellite could work. So I have one more slide about the sort of benefits that we have. Our community does a lot through FAST. And so this is great for building, testing, and flying new ideas. It's difficult if you want to use it for collecting data, because our data is actually more valuable the more years you have of it. So FAST is great for tech development, but not quite as much on the science side. It's been great for us for HQP, so that's just giving you a sense of the number of people who've been involved. For me, I cut my teeth on a balloon mission back in 2002, which was really helpful because I was also getting into a space mission at the time, so I had the end-to-end experience. And through our work in capability demonstration, this is really something we mainly do in collaboration with industry, but it's great for mission development. So the last thing is just to show, since Mick got to show his stuff, I have my cool view of looking down on beautiful Timmins in 2018 from a GoPro that we attached to our payload. And the reason that we did this was because we like to have small projects for the undergraduates. And so one of them was, hey, I want to fly a camera. Can you make that work? And so that was their task. So I'm going to stop sharing and say thanks very much.
Well, thank you, Kaley. That's great. Thank you. Anton.
Okay, let me just share my screen. All right, you should be seeing that now. Are you seeing my slide?
It's not in presentation mode, but I would just keep going.
Oh, you can see my slide or no?
I can see the PowerPoint.
PowerPoint.
Window, but not
Okay.
in presentation mode.
Okay. All right. Well, I'll in the interest of time, I'll continue.
Just keep going.
Yeah. So I'm a professor of aerospace engineering at Ryerson University, also a Canada Research Chair in Spacecraft Dynamics and Control. And so my current research areas, it spans astrodynamics and spacecraft, space robotics, and dynamics control. And my research areas right now are on-orbit inspection, servicing, and assembly of large space structures using free-flying robotic spacecraft. guidance, navigation, and control in proximity of irregular bodies such as asteroids, and low-thrust space trajectory design. The first one, the on-orbit inspection, servicing, and assembly of large space structures, is really motivated by the idea of assembling and then maintaining structures in deep space environments such as Gateway.
Anton?
And yeah.
We don't see the slides progressing.
Oh, no?
No.
Okay.
Oh, there we go.
Okay, I just got out of presentation mode, so I was in presentation mode, but
Yeah, okay.
I'll stay here. I guess it doesn't look that great, but maybe I
That's-
can minimize this.
Yeah, that will work fine.
This is the best I can do, I guess. All right, so yeah, on-orbit inspection, servicing, and assembly of large space structures. All right, so the idea is to assemble large space structures that are large, so large that they can't be launched in one piece, but to do this autonomously using free-flying robotic spacecraft, and then to maintain those structures, to be able to inspect those and service those, again, using free-flying robotic spacecraft, preferably autonomously. And so it's this particular research emphasis that I'm developing a test bed for in support of that, to try to mimic the it's out of all three, is really the only one that sort of is amenable to a test bed. The other two are more astrodynamics related, and so they're more simulation based. But the first one is to come up with a test bed which mimics the frictionless nature of space. So it's still under development, but I'll give you an idea of what that test bed looks like and what we're trying to do with it. So basically what it is it's a large 15 by 15 foot table with a very smooth flat surface. You can see it's being constructed on the left. It's now being completed, and on the right you can see the inside. The table, it's housed, it has a blackout curtain around it to block out ambient light. And inside we have free flyer spacecraft, which are floating on air cushions, which can then move in translation and rotation by one axis. So translation in the plane and rotation by one axis, and thereby mimicking the frictionless nature of space. For navigation purposes, above the table, we have an overhead LED star field, which is used for onboard navigation. So we want the free flyers to do everything autonomously, including their navigation. And so that's what we have the LED star field on the ceiling for. And because we have a blackout curtain, we obviously can't sit inside to monitor it. So we have an interior camera to monitor it externally at a control station. We are putting together 4 free flyer spacecraft, which will perform the functions of inspector, so performing inspections of structures, servicing those structures, so removing damaged parts and replacing them, and also for physically grabbing pieces of structure and manipulating and assembling them into a larger piece of structure. So these free flyers, they're equipped with upward facing cameras, and those are for navigation purposes using the star field above, which I just mentioned. And also have forward facing cameras for the purposes of inspecting a structure. Some robotic arms for repair and manipulation. It's got some docking mechanisms on board, so it can dock with structure or with each other. And some reaction wheels, fans, for the rotation and translational control. And finally, all communication is done wirelessly. And so the last part, so these are the inspector spacecraft. The last part is the actual structures that need to be inspected. And so for that purpose, these are not complete. These are still under development, but we have larger free-flying structures, which also float on the table, that are being created, and these will represent the structures that are to be inspected and serviced and assembled by the free-flying spacecraft that I mentioned on the previous slide. And it's not shown here just yet, but it will have configurable exteriors for these structures, so we can change the way they look on the exterior. We can create damage, which the inspector spacecraft will then need to be able to detect and to repair. And these ones will also have docking ports for the purposes of docking with it, or for grasping it to be able to manipulate. We have 2 of these pieces of structure, so ideally we aim to be able to capture these pieces of structure with our free flyer spacecraft using the robotic manipulators, and then bringing the larger pieces of structure together, and thereby mimicking an assembly type process. So obviously, in space, everything is going to be done with 6 degrees of freedom, but we can't mimic that environment here. So the best we can do is to do this in the plane, with 3 degrees of freedom, 2 translational and 1 rotational. I think that's all I have.
All right.
Yes.
That is perfect. Thank you very much, Anton. Philip.
All right. Thank you very much. I'll just share my screen here. Looks like you can see it now. Okay, let me start this here. All right, you can see my slides there, Daniel?
Not yet.
Not yet? Did it not go? Strange. It's showing to me that they are. Hold on, I'll try this again. Okay, can you see anything now? Looks like it's shared.
I cannot, but maybe that is particular to my setup here. Maybe Jeff or Todd can comment on this.
Yeah, is everybody's
Nobody else?
camera off except for Phil?
Yep.
I don't see anything.
I see
No?
a big gray
Okay.
screen.
Strange. Okay, well, I will. Okay, so I take it you don't see anything now either, then, right?
Now we
Okay,
see you.
it's all right. I can talk without slides. Who needs
Dan
slides?
and Phil, we can nibble away at the coffee break here. So Phil, we've got a few minutes to get.
Okay. Anyway, I'll get talking then. If the screen starts sharing, then just let me know. So my name is Philip Ferguson. I'm an associate professor of aerospace engineering at University of Manitoba. My research is somewhat similar to what Anton was talking about. I look into spacecraft guidance, navigation, and control, but I focus mostly on how spacecraft can control themselves if they're in an unknown dynamic environment. So if they're orbiting say a Lagrange point, or if the spacecraft has dynamics that are not very well understood. And so in order to do that, I really need to have full 3-dimensional dynamic simulation. And so while I would love to be able to do all of my experiments on parabolic flight or in suborbital flight, like we heard from Jenny earlier today, I need to have something in my lab that I can do that with. So I've created a test bed known as reset. This stands for the reconfigurable empirical spacecraft. And really what it does is it uses drones to mimic the dynamics of space. And so the idea here is that I use drones as a dynamic emulator, and underneath the drone, I attach a small spacecraft that is capable of 3-dimensional rotation and translation. And then the drone senses the motion of the spacecraft underneath it, and it provides the forces and torques that the drone or that the spacecraft would feel if it were in the dynamic environment that it was actually operating in. And so what's interesting about that is that not only can we simulate the kinds of parabolic flight, spacecraft aircraft are doing in that they're removing gravity, but we can also now start to mimic different kinds of dynamics that we do in parabolic flight or in suborbital flight. And so these are things like using the drone's controller, I can make the spacecraft feel like it's twice as heavy than it actually is, or a third as heavy as it is. I can make the spacecraft or the drone, if we're simulating drone dynamics, I can make the drone feel like it's flying through air that is 5 times more dense than the air on Earth. Or I can make it feel like even something very artificial, like there's an elastic band that's stuck to that spacecraft. So in this sense, we're doing what we call active emulation, where we are sensing the dynamics and then applying forces and torques to mimic that specifically. So recently what we've been doing is a lot of stability studies that demonstrate that this test bed can work. We've done some small scale single and double axis type experiments where we've demonstrated this to work, and so far so good. And now we're designing our own drone that we should be flying in the next month or so, that has 3-axis independent position and orientation control. So effectively what it is it's a cubic drone that has propellers on all sides of it with a small CubeSat on the inside. And this is where it'd be great to show you a picture of it right now, but I can't. And then that spacecraft that drone flies around the test bed with the spacecraft embedded inside. And then, like I'd mentioned before, so what we're using this for right now is that we're now able to, with that spacecraft feeling like it's in this virtual environment, but using real hardware to control itself around, we can now implement equations that make it feel like it's in an environment, say a relative space environment, where it's obeying, say, the Clohessy-Wilshire equations of two spacecraft in neighboring circular orbits. But what I'm focusing my research on right now is neighboring orbits about a Lagrange point. And we're looking at ways in which spacecraft can learn to control themselves in that environment, even in the presence of unknown dynamics. So that's my test bed. Thanks.
All right. Excellent. So I'd like to invite everybody on the panel to switch on the cameras again. And this is the time that I am looking forward to your questions. I have a few ones prepared, but I much rather have the questions from the audience. But we'll get it going, and then hopefully we'll see some questions pop up in the chat channel. So, can you explain? And it's pretty fantastic. I mean, we have a drone, we have a giant air hockey table, we have a sandbox, we have a balloon. It's awesome. It's fantastic. So, can you tell us something about one aspect of your system that is unique to building it or to maintain it? Something that we don't know that was particularly hard or challenging to realize. So, who wants to go first?
I can go first.
Okay.
So I'll lift up my screen, and you may notice something. If ever you've worked on rover analog missions, you don't want footprints, and there's no footprints behind me. So we have developed a proprietary technology to get rid of footprints on sand. It involves a broom and an army of co-op students. So that actually, I was actually just talking to one of our engineers just before going, and I asked them to clean up the moon yard because we had been using it pretty actively for some R&D. And I asked them how long it took. And so it took about 2.5 hours to completely get rid of footprints and also put in some of these craters. These are impact craters that are formed using various high fidelity projectiles, such as basketballs and tennis balls and things like that. And while that sounds, it sounds funny, I'm making a joke. It's actually our chief science officer, Melissa, who's a planetary scientist. These are real techniques used to kind of simulate what these features would likely be like on the moon. So anyway, I thought that was a fun anecdote to share.
All right. Anybody else that encountered a unique challenge realizing that testbed?
Yeah, I can talk. I mean, testbed is not finished yet, but for me, the biggest challenge is that the testbed is a complete custom design, there's nothing in the test bed that can be purchased off the shelf. So there's a lot of, we have to design everything and get quite creative with how we do that. So for example, the air tanks, those come off, you got those from a paintball supplier, for example. Yeah, so this together with the pandemic and the associated lead times now on getting components is what's taken us so long to get this test bed together. Just because we have to do the custom design first. There's no company that's doing that for us. We're doing that ourselves. But then once we have all the prototyping and everything done, then we can ship the final design off to the manufacturer, who will then manufacture the other pre-flyers, let's say. But yeah, no, everything, it's not just a matter of doing the design, it's a matter of doing the preliminary design, prototype building, testing, going back, redesigning, and so on. So for us, that was the big challenge. Yeah, can't get anything off the shelf.
All right.
Yeah, I'll jump in. I'll say also that one of the reasons why we make test beds is to create environments that are difficult, right? And I think when you do it right, and you find yourself now trying to control a vehicle in a difficult environment, you realize that you've really created a hard problem for yourself. And just as an example, the first time we simulated a microgravity environment using a drone, the drone went horribly unstable and crashed, and I had to buy myself a new drone. And my student came to me and said, "Oh, I've got bad news. I crashed the drone. I need to buy another one." And I laughed and I said, well, that actually makes sense, because a quadcopter, like a quad rotor drone, would not work at all on the International Space Station. A quad rotor drone requires gravity in order for it to work, because that's how it tilts itself to cause motion left, right, and up and down. And so the fact that we were actually experiencing what I think is something very real was interesting and somewhat unique too, because fundamentally we're simulating an unstable system. And those are hard, and so I think it really underscores the need for test beds like this across our industry.
And for us, I think I have a lot of combinations of what Phil and Anton have already talked about. The need that everything we buy the laser, we buy the optics, we build the computers, we build the systems. I'm lucky enough to have a gigantic vac tank that I can do TVAC testing in, which I happen to inherit from some previous Canadian space missions that happen to be in my department, which is great. It fits about 15 graduate students if you pack them right. So, it's a good 2 meters in diameter and about 5 meters long. So it's great because you can fit all sorts of different things in it, but that it gives you that one step before putting it on the balloon. Because, things like you go down to a 5 millibar from 1,000 millibar and you don't want your capacitors to blow up, for example.
Right.
And making sure that the detectors that need to have liquid nitrogen, the pressure fittings are working so that doesn't evaporate in the first, X number of minutes of your flight. So it's those stepwise thinking about how you can do this, because the balloon's a great test bed, but you usually get a chance to do that maybe once every 2 years if you have enough human power every year, but still that's only as frequent as you can do it. And I have an interesting observation about the quadcopters. At the Pro Lab in Eureka, we have one of our research scientists who has been using it to make measurements at different altitudes, and had to disable the system because the magnetic field lines, because you're so close to the pole, don't work the right way. And the quadcopter was just so confused. It also had some problems that its batteries really didn't like minus 40, so that had to be fixed as well.
Excellent. Well, those are great examples of the challenges that you're facing. And it's fantastic, all the things that you do to overcome them. We have one question, and I'd like to see more. So please don't be shy. This is a sand question, or in the technical term is a regolith simulant. What kind of moon sand are you using, Mick?
That's a good question. So we are very familiar with various types of soil simulant on the moon, or regolith simulant. We chose to not go with any of those for some very specific reasons. One, they're a health hazard. We wouldn't want to be wearing masks or anything like that, right? But yeah, it actually is a health hazard where we would need to enclose our whole system. Every time you would go into the facility, you'd have to be there's certain safety protocols you would need in place. So we chose, because our primary objective was to simulate the visual appearance for both computer vision, algorithm development and testing, as well as operations, we were able to get away with play sand. So what you would see in your regular playground, we had that shipped here, and we mixed in some kind of very fine-grained gravel to give it a bit of a grayer appearance there. So yeah, and we have some real rocks, but some of the larger rocks you see here are also, I don't think lawn ornament is the right word, but those sort of custom-made fake plastic rocks, because frankly, to move those things around would be just impractical. And so we wanted to really to have something that was reconfigurable and practical and usable, on a daily basis. So, yeah.
Great. Thank you, Mick. And also, I don't see any other questions from the audience, and I have one more. So if somebody in the audience, student or a researcher sees, well, I could really use this. I'd like to collaborate. I'd like to make use of your test bed. What's the right way to go about it? Who wants to go first?
Sure, I can start. I think most of us, I'll speak for myself. I've got a website, umstarlab.ca. My lab is called the Space Technology and Advanced Research Laboratory, or StarLab. And I'll throw it out there that I had that name before Nanorax used it. So. But anyway, you can reach me at umstarlab.ca and contact me. We're here to support researchers and industry alike. Thanks for that.
And Anton, if people want to use your giant air hockey table.
Yeah, just contact me. My email is on the Ryerson website. It's probably, is there proceedings or anything associated with this discussion?
Hard to find.
Well, in any case,
we'll include it if you'd like us to, Anton. No problem at all.
Oh, sure. Well, yeah, just any, through email is the best way to get a hold of me. I mean, I do have a website as well, but I don't remember the URL off the top of my head. But again, you can get through it through my departmental web page, which is ryerson.ca/aerospace. And so if you go there, you'll find me pretty quickly.
Okay. And Kaley, are there any funding mechanisms available? Because
So if you've got, yes, so balloons are cheap, but there are different ways to go in. One is to collaborate, be part of my team, or one of the other professors across the country or companies who are flying as part of Stratos. So you can get in that way. There also is a program through SEDS where you can apply. There was one this year for ballooning, there was one for microgravity, and there was a brand new one for Arctic, where teams of students with a faculty advisor propose to do an experiment, and you get evaluated and you could get selected. Typically, there's at least 2 teams that seem to get selected for the balloon ones each year, because usually when I've been in Timmins, there have been students on the SEDS program there. Also through ESA, because we're collaborating state of ESA, there are two programs called BEXIS and REXIS, which allow you to fly your thesis project. REXIS is on a rocket, BEXIS is on a balloon. They don't pay for the development costs, but they pay for you to get there. So you get to go to beautiful Kiruna's northern Sweden, a town that has been moved because the giant iron ore mine underneath the town was perhaps causing it to become unstable, so they've moved the town. The Arctic, or the launch facility is outside of that. Caribou is great. It's a good place to go if you can get in on that. So there's lots of different programs that students can apply into. And there's lots of opportunity. And the people for the Swedish Space Corporation are great to work with as well.
Okay. And Mick?
Yeah, well, we're a commercial company, so our facilities are, we're happy to work with different kinds of partners in different ways. We have supported academic proposals for FAST grants or, NSERC Alliance grants and things of that nature where, we might have a role to play and we can provide in-kind contributions, such as the use of our facilities or data sets. In other instances, it makes sense for us to be supporting those activities. So we're happy to work with folks to submit those grants and proposals. We also have more straightforward sort of commercial services. So what we do and what we do well is we develop software to automate and operate robotics. So we have a plug and play system where people can quite literally ship their rover or their lunar payload to our facilities here. We plug it in and they can control it remotely from their home, provide them with a URL for command and control of that payload. So we do that quite frequently. And we have sort of a commercial model around that. But we're always open to working with people in various ways. We understand that much of this stuff is R&D and you have to go out and get the funds to do the R&D. And so we're familiar with that process. So, happy to have people contact me directly. You can also go through our website. And we want this facility in use all the time. So if you're interested in using it, we're happy to work with you.
Perfect. Thank you very much, Mick. All right, then I have one final question and then we'll close the session after that. And that one is for Anton. Are you planning to take measurements on the actual grabbing forces in 3 degrees of freedom for the free flyers?
Yes. So initially, no, because we just want to get the test bed running and want to keep it as simple as possible. But long term, absolutely. Actually, in long term, I'm hoping to develop our own robotic arms and put those on and have all the sensing capabilities at the end effector, because those are important in reality. And some of the algorithms that we're developing do require measuring. They assume that those forces are available. So yes, long term we will be looking at taking those measurements, but in the short term, no, we want to get the test bed up and running first.
All right, thank you very much. All right, well, I think we're at the end of the session time-wise. Thank you, all 4 of you. Thank you for sharing with your fantastic test environments. It's really impressive. It was a pleasure moderating this panel. Thank you all, and I wish everybody have a great afternoon. Thanks.
Thank you.
Thank you.
Before everybody goes, just a question to all at once. Does anybody not want us to publicize how to get in touch with you? If not, we will make sure that information is available to all the participants in the conference. You're good with it, Mick, Anton, Kaley, Phil? Excellent. Okay, thanks very much. Everybody, thank you very much for your participation today. Daniel, thank you for moderating. And I think we'll now segue into the technical sessions, of which there are 2 starting now and 1 more following those, and then the day will end. I need to just mention tomorrow, because of the how relevant the space domain awareness workshop is going to be this week, because we're talking about what happened with the Russians having destroyed one of their own satellites. On the 15th of November. Space domain awareness is very apropos this event, and I recommend it strongly to everybody. It's going to take the whole afternoon tomorrow. So enjoy.